Now, we will talk about the convergence of Taylor polynomials. We have learned the convergence of sequences, right? And we have learned the series. If you have the series, how do we define the series? Define the series as the following. The summation k to n, k to infinity of k, of a sub k. This is the series, which is the limit n approaches infinity of the sequence of partial sum, which is the limit n approaches infinity of the summation k from 0 to n of a sub k. Right, this is the series. So now the nth Taylor polynomial is given by p sub n, which is the summation k from 0 to n of f, the k's derivative at x naught over k factorial times x minus x naught to the power k. Right? If we let the derivative and the limit n approaches infinity of p sub n, so this is it's equal to k from 0 to infinity x to the k's power x naught over k factorial x minus x naught to the k's power. If the limit of p sub n, the nth polynomial, Taylor polynomial, is equal to this f of x, then we have this result: fx is equal to the summation k from 0 to infinity f of k derivative at x naught over k factorial x minus x naught to the k's power. Right? Then we can say this formula give a name which is called the Taylor series expansion. This is a series, right? This is called the Taylor series expansion. So in other words, if we denote this by star, if this star holds, if and only if the limit n approaches infinity of p sub n of x minus f of x, this limit is equal to 0. So in other words, the remainder r sub n is equal to 0. The limit of the remainder equal to 0. Right? If the limit of the remainder equals 0, then this star holds. Okay, in other words, you have this one. Right? The question is, so we always say this series, this Taylor series expansion converges to this f if this remainder have the limit 0. So we say this Taylor series expansion converges to f if the limit of the remainder equals 0. So in general, this f of x may not be equal to this Taylor series expansion. Even the case derivative always have the case derivative. This may not be true, right? So we must have some criterion to identify if this function can be written as the Taylor series expansion. So we will use the Lagrange remainder theorem to prove that criterion. Before that, we need to look at one result. So now let's look at this lemma. The limit n approaches infinity of c to the n over n factorial is equal to 0. So here c is any number. So this is the that means this limit means the n factorial grows faster than c to the n. So now let's look at the proof. Okay, we choose k be to be a natural number such that k is greater than or equal to 2 times the absolute value of c. Then if n is greater than or equal to k, then this one, n factorial, it can be written as the product of two parts. This would be the absolute value of c over 1 times the absolute value of c over 2 times the absolute value of c over k. And here is the absolute value of c over k plus 1 times absolute value of c over k plus 2 times, continue, times the absolute value of c over n. So the denominator will be n factorial, right? We divide into two parts. Then the first part, the first product is less than or equal to the absolute value of c to the power k, right? We decrease the denominator 2, 3 to k to be 1. So you have k's power. Over, we use this inequality. Then we can see this one is, each one is less than or equal to 1/2. So there is 1/2. How many terms we have? We have n minus k terms. If you rewrite this one as for a better understanding, so this is 2 to the k's power times 1 over 2 to the n's power, right? You can see that if the limit and this limit n approaches infinity, this would be 0. So that means the limit n approaches infinity of c to the n over n factorial, this would be 0. This is by the definition of the limit. So we finished this result. Then we want to look at the criterion to identify if a function has a Taylor expansion, Taylor series, has a convergent Taylor expansion.